All right, so we're now going to start looking at forced second order systems. So we're going to use the same process or system as looked at before. So here's this one, y double dot plus 6y dot plus 18y. And on the input side, instead of having it 0, we're going to have it be 9 f of t being the input, where we have initial conditions y 0 equal 2, y dot of 0 equals 4, same as last time, and the input is equal to a unit step, u of t. All right, so we're going to take this opportunity to define another characteristic of a differential equation, uh, the kind that we're playing with, and that's the term called static gain. So we'll just pull this down. Uh, Static gain is the value of gain k in the equation output equals k times input when the derivatives of the output are set to 0. So that sounds really weird and everything. So what does that mean? So if you look up here, if I set this derivative to 0 and that derivative to 0, I'd be left with 18 times y, which is an output thing, equals 9 times the input. And so here's the idea: is we wipe these out, you bring the 18 to the other side, you'd have y equals 1/2 times the input. That 1/2 would be the static gain. That's what's shown right here. 18y equals 9f of t. Bring the 18 to the other side, you get y equals 1/2 f of t, the static gain. You might ask, well, what's the importance of that? Very simply, when you have an input, a step input, the static gain is the gain applied to the step input at steady state. So if you apply a unit step input and the static gain is 1/2, your steady state value will be 1/2. So that tells you where you're going to end up. Okay, if your step input had a magnitude of 4 times 1/2, let's say you'd expect an output of 2. So that's what static gain tells us. So here we're going to go solve this system now. We've got y squared plus 6 lambda plus 18. So we already know the roots are -3 plus or -3i. We noted previously that rather than use our other pattern we were using for a complementary solution, we can use this one. We still have to have two constants to solve, but now we're just going to have an amplitude and a phase. Okay? So when you go to, so this is what our complementaries look like. We have a step input. So once again, it's just here will be for step input, the form of the particular will be simply some kp. So we stick that in. The first and second derivatives are 0, and we wind up with kp is equal to 1/2, same as static gain. All right. Therefore, the total solution will be the particular plus one complementary. And of course, we could always break this down into two complementaries, where one is the initial condition response and the other one combines with 1/2 to be the forced response. We're not going to do that here. So here's the total solution we're going after. And so we simply set y of 0 equal to 2, because that's one of our initial conditions up here, equals 1/2 plus, let's let t be 0, so you wind up with a cosine phi. You can solve for a cosine phi. It's 3/2 from what we have here. We take the derivative. Y dot of 0 equals to 4. All right, so we take the derivative of this and set time equal to 0. We wind up with -3a cosine phi. The -3 comes out here, -3a, e to the 0 is 1, and then we just have cosine phi in the center. And if we take the derivative of this one, that would be leaving that constant. Anyway, you wind up with -3a sine theta. All right, so a cosine theta equals 3/2. Here's a cosine theta times -3, so that's minus 9/2 minus 3a sine theta equals 4. All right, so we can move this to the other side, gather terms, and here's what we're left with. When we bring the 9/2 to the other side, we have a sine theta, and there's a minus sign here, let's note, and you got this 3 here to bring to the other side. So a sine theta is minus 17 over 6. A cosine theta is 3/2. All right, so we now say this squared plus this squared is a squared. And then we will form a tangent, sine over cosine, inverse tangent, whatever that is. All right, so we take these two, square them. Here we get a. We take the a sine phi over a cos phi, so it'd be minus 17 over 6. And 3 over 2. And so this leaves us with minus 62.1 degrees here, times pi over 180 to make it radians. And we already have that gain. And so here's the total solution. We have a half. This is our steady state solution plus, and this is what attenuates. 3.21 e to the minus 3t, that's what's going to attenuate everything. And here's this cosine wave, 3t minus 62.1 degrees pi over 180. And if we were to plot that, here's our steady state at 1/2. Okay. We have the roots, we're at minus 3. Okay, so we flip that, we get 1/3 times 4, so here's our settling time. Here's the steady state value, and we're going to get some overshoot. And this frequency here is 3 radians per second. So if we look at this, and we can kind of sketch that out very easily. All right, so then we're going to do another one. There was a step input. So now we're going to do a ramp input. All right, so for a ramp, this is the exact same problem. I'm just changing the input here, making it into a ramp. All right, so to do that, I'm going to use this as my complementary solution again. Gives me the two, I have to have two constants. I have them. All right, but now with the ramp, here's my particular solutions, some k0 plus k1t, which we have to solve for. So we stick this in, we take the second derivative, there'll be nothing there. First derivative is just going to be a k1. So we have 6 k1, and then we have plus 18 times the full thing, that's right here, equals 9t. So if we equate the t terms, we have 18 k1 equals 9t, so k1 is a half again. Or k1 is a half, or once again, we're seeing that 1/2 term show up. We equate the term t to the 0, which there's nothing on this side, so 0. 6 times 1/2 from here, plus 18 k0, what we want to solve for. We get k0 is minus 3 over 18. All right, and so sticking all that in, we get y of t equals, so here we are, minus 3 over 18. That's like a step portion. Then we have our ramp portion with 1/2. And now here we have to figure out what the complementary solution is to take us from these initial conditions to this steady state response. So it's the same gig. y0 equals 2. Solve for that. In this case, a cosine phi is 39 over 18. Just bring this over here, and you should, that'd be a 36 plus 3 over 18. So there you go. Now we have y dot of 0 equals 4. Same initial condition. So we take the derivative of, let's take the derivative of this, we get a half. All right. Well, then we have two parts for the derivative of this. We'll get a cosine phi portion and a sine phi portion as we take the derivative of that. Okay. But we know a cosine phi, so we can stick that in and solve. So here we have this, that goes in here. Then we'll have numbers for this, this, and that. We'll gather the terms. Then we have minus 3a sine theta, then equals everything else. If you're moving everything over, a sine phi is minus 10 over 3. So this is just simple algebra. But now we're once again back to a cos phi, a sine phi. So this squared plus this squared square root gives us a. That's right here. Then a sine phi over a cosine phi is tangent of phi. So we'll do an inverse tangent, and we get minus 57 degrees times pi over 180. Now we just stick that in. Minus 3/18 plus a half plus 3.98. That was our a. E to the minus 3t, that attenuates. Cos 3t minus 57 degrees, pi over 180. And we have that one now. And I'll end this video here.